Now that we have mastered the art of the equilibrium constant and ice tables, in this unit and in the upcoming units, all we're going to do is apply that to different types of equations, different types of reactions. Here we're going to look at solubility. Early in the course, we had talked about precipitation reactions, and there was this solubility chart. Oh gosh, I think it's like chapter 4. And some of the substances are listed as soluble, highly soluble. Something like sodium chloride is obviously very soluble. So if I wrote like a little equation for the solubility of sodium chloride, I would be thinking that if I took sodium chloride solid and I throw some in water, it would totally ionize or dissociate to form sodium ions, AQ, and chlorine ions, AQ. And we say that the sodium chloride ionizes 100%, or that it's fully ionized. So that if you took 1 mole of solid sodium chloride and added it to enough water to make a liter of solution, if this were like 1 mole per liter, well, by the time that entire sample dissolves, you would be left with a full mole of sodium ions per liter of solution and 1 mole of chlorine ions per liter of solution. And eventually, this solid is gone. It 100% fully ionizes. This goes forward 100%. And so at the time, we were only talking about these one-sided arrows because the reaction went forward, it made products, and then eventually it stops. Yeah, well, that is somewhat true. And with something that's highly soluble, even though you've got these sodium and chlorine ions that are now swimming around in the solution, if sodium chloride is 100% aqueous, even if these ions collide with each other, they never form a new compound. As soon as they would maybe want to collide and form NaCl, it's like, well, nope, we're totally soluble. In the presence of water, we're going to stay dissociated. And so when you eventually look at these dissociation equations, they do have K values. They do have equilibrium constants. It's just that for something like sodium chloride, when we say that it dissociates fully or it goes forward 100%, the K value is huge. And so often we don't even talk about it because the chance of this thing going in reverse is like 0 to almost none. We use a one-sided arrow and we just say, yeah, that sodium chloride is 100% soluble. It goes forward and you get 100% formation of ions. Cool. But it's not the case with all solids. Not all solids fully ionize or stay ionized. And so, for example, here is some calcium fluoride solid. So when calcium fluoride solid is in water, it dissolves and dissociates to form calcium plus 2 ions and 2 -1 fluorine ions. Awesome. But when you have something that's not 100% soluble, this, number one, may not go forward 100%. So that if I did have 1 mole of calcium fluoride, if it's a solid that's only slightly soluble, it might not give me then 1 mole of calcium and 2 moles of fluorine. Not if it doesn't dissociate 100%. Also, in some of these situations, you may have the calcium and fluorine ions swimming around in water, but if they collide, if it's not something that's highly soluble, they may collide and then shift this thing in reverse so that they go back to the original calcium fluoride solid. And so you can get an equilibrium system. But usually this is only for things that are slightly soluble or marginally soluble, where you might go forward and make ions, but then some of those ions could collide and shift it in reverse, going back to the original solid. And this thing probably doesn't go forward 100%. That's kind of what we're looking at here. I mean, the things that are highly soluble, like your sodium chloride, sodium nitrate, like anything with an alkali metal, nitrates that are highly soluble, that's like this situation in blue and orange, where we don't even usually talk about their equilibrium constants because they're ginormous and this thing isn't going to reverse itself anyways. Even if sodium and chlorine collide, they just split apart immediately. Not always the case. So we're going to focus in this little mini unit on solids that are only slightly soluble. We're going to look at their equilibrium expressions and some ice tables that we can set up. And so here, the equilibrium expression looks just like what we might expect, that our equilibrium expression is products over reactants, but I'm not going to use solids. So I'm not going to use this guy, he's a solid. So I'm really only going to have the two ions. I'm going to raise their concentrations to the coefficient in the balanced equation. And this then is really all I need for my equilibrium expression. Products over reactants, but I'm not going to use the reactant, it's a solid, and then I just have to square the fluorine. All of these reactions are going to look really similar. It's going to be the tendency of some solid to dissociate forward and make ions. And so you're always just going to have an expression that looks like the product of the ion concentrations, and we're never going to use the solid. That is why this is often called the KSP. KSP just stands for solubility product, or sometimes they'll even refer to it as an ion product, because that's exactly what the expression is. It's a product of the two ion concentrations. And I do just need to then like square my fluorine, or I have to pay attention to any coefficients from the balanced equation. So we had like Kc, that was when the equilibrium constant was calculated with concentration. Kp represented pressure. Now we can have Ksp, solubility product. All right, so here's my equilibrium expression. Now, let me show you two different types of ice tables that you could run into. Ice table numero uno, calculations with solubility. We could have some copper 2 bromide that has a measured solubility of 2 times 10 to the negative 4th moles per liter at 25 degrees. And I want to calculate its K value. Okay, so here's one thing we could do. We could calculate an equilibrium constant. Well, let's set up the ice table. So I've got copper 2 bromide. Well, that 2 is just telling me that copper's charge is +2. Bromine is a -1. So I'm going to have something like copper. I'm going to need 2 bromine, Br2. And then when we set up these equilibrium reactions, we'll use a reversible arrow. Look at that measured solubility. So I can only dissolve 2 times 10 to the negative 4th moles per liter. That's not much. All right, so then if this dissociates, I could put this into as a solid. It would be like the original solid. It would form copper plus 2 ions, aqueous. And then I would get 2 -1 bromine ions, AQ. So all of your equations are going to just be these dissociation equations. And then we're going to ICE. We're still going to set up these ice tables. All right. So now they're giving us this measured solubility. That is often referred to as like the maximum solubility. The maximum amount of copper 2 bromide that I can dissolve in water is 2.0 times 10 to the negative 4th moles per liter. Now, if they ever ask me, like, what is the maximum mass that I could dissolve, well, then I would just take 2.0 times 10 to the negative fourth moles of copper 2 bromide and turn it into grams. And that would give me the maximum mass that I could dissolve in 1 liter. Or if I had 500 milliliters, I would just divide in half. This is the maximum you can dissolve. And if you have that maximum amount dissolved, we say that the solution is saturated. So a saturated solution just means that you have dissolved the maximum amount it will hold. A way to tell that your solution is saturated, if more solid is added, it will not dissolve. It will not dissolve. So if I'm not sure if my solution is saturated, you say, I think I got the right amount in there. I'll just try adding a little extra. If it dissolves, then nope, you didn't hit that maximum solubility yet. But if you add a little extra, like if I add more than 2.0 times 10 to the negative fourth moles of copper 2 bromide in a liter of solution, it will not dissolve anymore. And instead, it's just going to sink to the bottom as a solid. So if you ever have a solution and you see a solid on the bottom, then it means that the solution is saturated. It has dissolved the maximum amount it can hold. Okay, so here's the deal. I don't know any of the initial amounts, so you're like, how on earth am I going to start this ice table? Well, we're starting with solid. We're going to start with solid, and we want to know its tendency to go forward and make ions. Well, originally we're going to have some solid, but initially I guess I don't really care how much. So I'm just going to scratch that because I'm not going to use the solid in my calculations anyway. I've got a whole bunch of solid, and initially I'm going to put in these ions as 0. I don't have any ion. I'm going to start with solid. The one number that I could put in, though, is that when I put this amount of solid in water, the maximum amount that'll dissolve, any amount could go down by 2.0 times 10 to the negative fourth moles per liter. So whatever amount I start with, that's the maximum amount that will dissolve and dissociate to form ions. So if this is the maximum amount of solid that dissolves, then I just shift this forward by the ratio in the balanced equation. So I would be able to form 2.0 times 10 to the negative fourth moles of copper ion per liter. And I just have to watch the ratio from the balanced equation, because then I would form 4.0 times 10 to the negative fourth moles of bromine per liter. So maybe that's the one number that I can put in under the solid. I'm not going to use it, but whatever amount of solid they gave me, I know that that is the maximum amount that'll dissolve to form ions. And so then, yeah, I'm just going to shift it forward by that 1:2 ratio. I'll form twice as many bromine ions as copper ion. Really, so that at equilibrium, again, I don't care about the solid. I don't care how much solid is left over because I'm not going to use it. And so then at equilibrium, this just would be 2 times 10 to the negative fourth moles of copper per liter, and 4 times 10 to the negative fourth moles of bromine per liter. Awesome. From here then, you can calculate the equilibrium constant. So K equals products over reactants. So it's going to be my copper plus 2. There's just 1 mole of it. So, I mean, if you want, you can put it into the first. And then my bromine. But I'm going to have to square that. So here's like my equilibrium expression. My 2 products, and then I raise the bromine to the 2nd power. Now, all you got to do is sub those numbers in. And then we're done. So we would just say K or KSP equals my copper 2 times 10 to the negative fourth to the first times my bromine 4 times 10 to the negative fourth. And that one I'm going to have to square. So sometimes people will forget to square it because they're like, well, I already doubled it in my ice table. But you still have to square it in your equilibrium expression. Now you just plug this all in and out comes your constant. KSP is about 3.2 times 10 to the negative 11th. And it's still unitless, so this is just it. You're done. And now this does make sense too because it's small. And so by saying that only like 2 times 10 to the negative fourth moles will dissolve in a liter, I mean, if you wanted, you could switch that to grams and it should be really small. There's not a lot of copper 2 bromide that's going to dissociate. And so now I can see that as well by having a really small KSP value.